Okay, chapter 2, this is the basic. They're going to start from smallest and going larger as we go. Okay, so we'll start with the chemical level, the molecular or chemical level, and then we will go to the cellular level, tissue level, okay, and we will go up until we go to the systems. So chemical level of the organism. So what are the atoms? The atoms are the smallest unit that have the characteristics of the element. This is the smallest that still have the characteristics of the elements. The molecules are a group of atoms that are held together by chemical forces. The proton, is it positive or negative? Positive, yeah, the P goes with the P. Proton, positive. Proton, positive. Neutron, positive or negative or neutral? Neutral is from the name, right? Neutron, neutral. Electron is negative. The mass, which is like kind of like the weight, the proton is one mass unit, the neutron is one mass unit, the electron is very low, enough that we even neglect it. It's negligible, so we don't even count. So if you wanted to count the mass number, you only count for neutrons and protons. Don't count the electrons. When you're talking about the charge, this is different. The electron does have a charge that's important. Proton, neutrons, yes. But from the mass unit, you're talking about protons and neutrons only. Okay. So what's the atomic number? The atomic number is the number of protons, okay? And these are things that are important to remember. Definitions, what's the atomic number? It's a number of protons. What's the mass number? This is the mass. What have a mass in the atom? What have mass? Do the electrons have mass? The protons and neutrons. We consider the electron don't even have a mass. Is it really nothing? Close to nothing, but so we ignore it. Okay? So what's the mass number? Protons and neutrons. Atomic number, protons only. There is a nucleus. The nucleus contains the protons and neutrons and surrounded by the electron clouds which contain the electrons. If you look at this, hydrogen 1, 2, and 3. Hydrogen 1, this is a normal one. We're supposed to, for the atoms, you're supposed to have number of the protons is the same number as neutrons, is the same numbers as electrons. And there are some exceptions. So if you're looking at hydrogen, you have one proton and one electron. Hydrogen 2, which is the deuterium. What 2 means here? Can somebody tell me what 2 means? The mass. 2 is the mass. So obviously, it's one proton, one neutron, and one electron. But the mass here is 2. Is it still hydrogen? Still hydrogen, because you have one electron outside. 3 means the mass is 3. You have one proton and you have 2 neutrons. So, what is fixed here? Protons does not change. Electrons does not change. What can actually change between the different structures are neutron. You either don't have a neutron, normally you have one, you might have 2 or more. Okay, so you're changing the mass. What didn't change here? Which is called? Atomic number, yes. So the atomic number does not change. The mass number does, because the neutrons change. So this is the percentage of the body weight of each one of these molecules. Oxygen is about 65%. I'm not going to ask you about these numbers, but just understand that oxygen, carbon, and hydrogen are the main things. Okay. These are the main elements. Oxygen is the main one, obviously, 65. And then carbon and hydrogen. Other things are nitrogen, calcium, phosphorus, and potassium. These are other elements, and each one of those has a function. Nitrogen is in proteins and nucleic acid, calcium in the bones and teeth, phosphorus, same thing, but it also works in the energy compounds. Potassium, sodium, both of those are important for the nerve signal that we will talk about later on. Chlorine is for the body volume, magnesium, enzymes, sulfur for proteins. So these are all small amounts. The main ones are oxygen, carbon, and hydrogen. Otherwise, everything else is needed in small amounts. Iron, for example, is important for carrying oxygen. Iodine is important for the thyroid hormones. And there are trace elements that's needed in tiny amounts. Basically, these are cofactors. If you remember what are the cofactors, it's the helpers of the enzyme. Okay? The element is determined by the atomic number. What's atomic number again? Atomic? Protons only. Mass? Protons and neutrons. Don't forget this. What are the isotopes then? The isotopes are different versions that have different mass number. So what's changing here? Is it the electron, the proton, or the neutron? Neutrons. Okay? So the isotopes have different mass number. This is a difference. How about the protons? Electrons? You can't change. If you change the protons, you're talking about something else. Okay? If you have one proton, it's a hydrogen. Right? You have one proton, it's hydrogen. One neutron, it's hydrogen. Two neutrons, it's also hydrogen, but an isotope. Right? Did you get this? So the atomic number does not change. If you change the atomic number, you're talking about something else. It's not hydrogen anymore. But if you change the mass number, that's fine. It's an isotope. So the isotopes will have a different mass number, but the same atomic number. They have different neutrons. Atomic weight, this is something else. It's not the same as atomic number. It's not the same as mass number. It is the exact mass of the particles, and they call it the average of the mass number of isotopes. Like if you look at this. How many neutrons here? Nothing. And here is? What's the average? 1. Okay? So 1 is the atomic weight, the weight of the atom. The average of the mass number of the isotopes. Plus the protons, I'm sorry. Neutrons plus protons. It's the average of the mass number. Okay, so outside of the nucleus, we have electrons, and as you know, the electrons are going in shells, 1, 2, 3, 4, depending on the number, and each one of those has a capacity that has to be filled first before moving to the next level. And this is called the outermost one is called the valence shell, and this the number of electrons per shell is the periodic table, and we're not going through the details of the periodic table. This is what we have to know. How many electrons can fill the first shell? 2. So if you have 1, it will go to if you have 1 electron, go to the first shell or the second shell? The first shell. If you have 2, first. If you have 3, 2 to the first and 1 to the second. Right? What if it is 9? How many in the first and how many in the second? First 2 and second? So if it is 6, if it is 8, it's 2 and 6. Okay? If it is 9, it's 2 and 7 and so on until you fill it. So if you go to 2, that will change to helium. And this is something different. How many can you add to the second shell until you fill it? 8. So this is full. Usually, all the regular atoms do not have shells that's full, and these are called reactive elements or reactive atoms. Why is it reactive? Because all atoms tend to fill the shells. They try to fill. If it is full already, like the neon, this is an inert or irreactive or non-reactive element. It's not looking for anything. It does not react. Why? It's full. So the atoms tend to fill their shells. Let's say 8 for oxygen. 8. How many in the first shell? Is it full? Okay. How many in the second one? Is it full? No. How many do you need? So the oxygen is reactive. And the oxygen will be looking for something to react with in order to gain or share in order to get the second shell full. How many do you need to fill the second? You have 8, so how many in the second shell? How many do you need?
16.
The oxygen is 8. You have 2 in the first one. How many in the second one? 6. It's 8. 2 and 6, right? Is 6 filling the second one?
No.
How many do you need to fill it?
8.
So what's the difference? 2. So you need 2. So here is oxygen reacting with 2 hydrogens. Is that okay now? What if I reacted with one hydrogen? Is that enough? No, it's still reactive. It's not enough. Okay? How many in the outer shell of the hydrogen?
1.
The hydrogen have only one shell, one electron. So you only need 1. Is the hydrogen reactive or not? Reactive? How many does it have in the shell?
1.
1. How many do you need?
2.
So what's the difference? 1. Right? So the hydrogen is reactive. It will be looking for something else to gain, to take electrons, or share. You don't have to actually take. You can also share. But the goal is to have the outer shell full. If it is full already, it's an inert material, inert element, like the neon is not reactive. Okay? Anything else is actually reactive. It's looking for something else to react with in order to get the outer shell full. This is the goal of any reactive element. This is gold, so it goes like 2, 8, 18, 32. Now the chemical bonds. And this is very important. What are the types of the chemical bonds? What are the chemical bonds first? These are bonds between 2 different atoms, 2 or more different atoms, and the goal is to get the outer shell full. Okay? We have different types of chemical bonds with different degrees of strength. Is it strong? Is it average? Is it weak? Okay? Covalent. Covalent is the strongest type of bond. Okay, and this is important. Covalent is the strongest type of bond. Okay, followed by ionic. The weakest is hydrogen. So covalent, strongest, and covalent means sharing. This is the sharing one. Ionic will be the next, and the weakest is hydrogen bond. So the hydrogen bond is very weak. You can easily separate the 2 atoms that are making the hydrogen bond. It's hard to separate the covalent bond. Okay? So when we say covalent means sharing, here is an example. I'm oxygen. Okay? How many electrons do I have in my outer shell? 6. How many more do I need to get my shell full? 2. Here is one hydrogen, and here is one hydrogen. Okay? Here's what I'm going to do. I'm going to give me your hand, just like this. Okay? So I have one electron, and she will have one electron. If we can do like this together, sharing. So I'm using her electron, and she's using mine. This is called sharing. And as long as we're sharing, we cannot separate. I need her, she needs me. If I separated myself, I will have my outer shell that's not full. Okay? So I have to do like this. I'm sharing electron with her. So is she okay like this? When she share my electron? How many she's having now? 2. Is that okay? Yes. So she's fine. I'm not fine. How about this? I'm going to share with her. Just pretend. Okay? So like this. So I'm going to share with her. Is she fine? Yes. She's using mine. So now she's having 2 in her outer shell. Is that okay? She's fine. So now I'm fine too. Right? Because I'm sharing 1 with her. So now I have 7. Sharing what from here? I have 8. Is that okay now? This is water. This is water. Okay? Are we sharing equally? Oxygen versus hydrogen. Are we sharing equally? She's sharing 1 only and I'm sharing 2. Are we equally sharing? No. So we have different types of sharing depending on are we equally sharing or not. Okay? So if you're talking about this, let's say oxygen was oxygen. He is oxygen, I am oxygen. How many do I need? How many does he need? How about this? In your hand. I'm sharing my 2 electrons with him. Is he okay now? He's 8, right? Am I okay? Yes. Is that equal sharing? Yes. We both shared 2 electrons. But in the first scenario, like in water, we're not equal. So the covalent can be equal sharing versus non-equal sharing, and we will come to this point. But remember, because you're sharing, you cannot separate, and this is why it's the strongest type of bond. Why? Because I need you, you need me. I cannot move away from you, otherwise I will not be stable, and you cannot separate because you will not be stable. So we have to share, we have to stay with each other, and this is covalent bond, and that's why it's the strongest of all. On the other hand, this is the first one, covalent, and we will talk about more details. The second type is called ionic. The ion means if you lose or gain 1 electron from the outer shell. So some atoms are able to share, are able to lose, and some are able to gain. Okay? Look at this, for example. This is sodium. Is the inner shell complete? Is it complete? Yes, it's 2. How about the second one? How about the third one? No, there is 1. How many do you need? 17. You need, yeah, the total is 18. So you need more 17. How about this? Look at this. Is the outer shell full? It needs 1 more. Here's what I'm going to do. Okay? I am sodium. I'm having 1 at my outer shell. I'm not going to share. I'll give them. Okay? I am losing electron now. Okay? Did I lose any protons? What's now more? Do I have more protons or neutrons? What do you think? Did I lose any protons? Did I lose electron? So which one is more? I have more protons. So now I'm positive, right? Because I have more positive than negative. How about him? Does he have more electrons or protons? Electrons. So he's negative, right? I'm positive. He's negative. We will be attracted to each other. I am an ion because I lost 1 electron. He is an ion because he gained an electron. So whether you gain or lose, I called you an ion. I am a positive ion because I lost an electron and I have more protons. He is a negative ion because he gained 1 electron and now he have more electron than neutron. So now he is negative, I am positive, and negative with positive, they attract to each other, and this is the, thank you, and this is the ionic bond. Did we get this? This is sodium. This is chloride for this example. I'm sorry, it's chloride. So sodium is losing one, chloride is taking. So obviously sodium is a positive ion and the chlorine is a negative ion. Since those two are, one is positive and one is negative, this is like a magnetic field. They will come to each other, not as strong. Why? Because I lost my electron, I can move away. I'm fine, right? Am I having my outer shell full already when I lost one? Yes. So I don't have to stay within. What's attracting us together is negative versus positive charges. So we can stay together. So, and this is the example of table salt. What's a table salt? Sodium chloride. What happens if you add some water to the sodium chloride? Dissolve, right? So can it dissolve? Yes. It's not as strong as covalent because just attraction, just an attraction. So this is the second type, which is the ionic bond. The third one is the hydrogen bond, and this is just a weak polar bonds that will depend on the partial electric attraction, and I will show you exactly what I mean by this, by hydrogen bond. Now what's the difference between molecule, okay, and compound? Molecule is two or more atoms joined by a strong bond, which is basically covalent. Okay, so two or more atoms joined, you call it a molecule. Compound, same thing, but they have to be different. Okay, so H2, is that a compound? Is it a molecule? Yes, it's two. Any two together, you call it molecule. Any two atoms, two or more atoms together, you call it molecule. Irrespective if H and H, so that's H2, or sodium chloride, it doesn't matter. Okay, but for the compounds, it does matter. It has to be different. Okay, so H2, is it a molecule or compound? Molecule. Is it a compound? No, it's not a compound. H2O, is it a molecule? What's the molecule? Any, not necessarily, any two or more atoms bound together. Anything. Did I say they have to be similar or different? I didn't say anything, right? Any two or more, or any two or three. H2O, is it two or three? H2, HHO, H2O. What's H2O? Two H's and one O, right? These are three atoms held together. Is it a molecule? Yes. Is it a compound? Yes. So H2 is a molecule, not a compound. H2O is a molecule and a compound. Did you get this? Molecule, we don't have rules. Any two or three come together, that you call it molecule. If the atoms are similar, it doesn't matter. If the atoms are different, it doesn't matter. Anything. But in order to say a compound, they have to have different. They have to be different. Okay. Now the ionic bond, the electron donor, is the electron donor will be positive or negative? Like sodium, I donated to him. Am I going to be positive or negative? Positive. And the acceptor is? Okay. So this is sodium chloride I was just talking about. Now the covalent bonds. We have some details to know. One hydrogen reacting with one hydrogen. Okay? This is equal sharing, right? How many electrons did you share? One. Hydrogen is one. Okay, this is the simplest thing. Hydrogen is one, just one electron. So if those two, I'm giving you examples, the two students are hydrogen, and they are reacting with each other. How many pair of electrons they are sharing?
Two. One.
One pair, or one each. So this is called single covalent bond. When I reacted with him, oxygen, How many did we share? So what do you call it? Double covalent bond. How if we're sharing 3? Triple covalent bond. So depending on the number of electrons shared, you call it single, double, or triple covalent bond. Covalent bond, still covalent, still sharing. How many are you sharing? Did you get this? Any question? So what? This is single or double or triple covalent? Yes? It's double. Okay, and that's why you see this bond here. This is single, this is double bond, another double bond. So for the carbon is sharing 4, okay, but 2 and 2. Now, polar and non-polar. This is what I was just talking about. When I say oxygen and oxygen, how many was I'm sharing? And he's sharing? Are we equal? Yes. Okay. This is called non-polar. This is called non-polar covalent bond. Okay? It's what do you mean non-polar? I mean there is no polarity. What's the polarity? Polarity means one is more than the other. This is called polar. Polar means unequal. Polars mean unequal. I have something here, I have something different here. This is polar. Was that polar or we're sharing equally?
Sharing.
Equally. So what do you call this? Non-polar. In this case, I was sharing with them. I'm sharing 2 and she's sharing 1. Are we equal? No. So this is called polar. So is the water polar or non-polar? Is oxygen and hydrogen sharing the same number? Or oxygen is sharing 2 and hydrogen sharing 1? So this is equal sharing or unequal sharing? Unequal. So what do you call unequal? Polar. Did you get this? So water is a polar compound. Okay, so here is the point of the hydrogen bond to understand it. I am oxygen. They are hydrogen, right? We are not equally sharing. I'm sharing 2 and they are sharing once. I'm sharing 2 of mine. Because I'm sharing 2, I will become slightly negative. Okay? When I share 2, I will become slightly negative. They share 1, they will become slightly positive. So look at this. Oxygen, hydrogen, hydrogen. Oxygen, hydrogen, hydrogen. The 3 of us here are polar because I'm sharing 2, they're sharing 1. Same thing here. Okay? So here's what's going to happen. She is slightly positive because she's sharing 1. Okay? And he's slightly negative, right? They will attract a little bit, just a little bit, slightly. This is completely different than when we say sodium and chloride. This is donating, okay, or covalent bond. The covalent bond is sharing. This is not sharing. And I said if I'm sharing more, it's polar. It's not equal sharing. I'm sharing more, so I'll become slightly negative. She's sharing less, so it will become slightly, not positive, slightly positive. So slightly positive with slightly positive hydrogen with slightly negative oxygen, you will come together just a little bit. Just heat it, and you will see the water evaporating, right? Why? Just give it a little bit of energy, and they will separate right away, because this is weak. This is a hydrogen bond, so H2O, H2O, the H will attract a little bit to the O. H2O here, H2O here, H2O here. This is the water altogether. And it's held together as you see it, the way you see it, by hydrogen bond, which is a weak bond. Are we following so far? So this is the hydrogen bond, and it depends on the partial attraction. So this is slightly positive with slightly negative. In this case, the hydrogen bond in water, This is slightly positive hydrogen with the slightly negative oxygen. They come closer to each other, just a little bit of attraction, partial attraction, and this is called the hydrogen bond, and this is the weakest of all. So look at this here. The red is oxygen, slightly negative, and the blue is hydrogen, slightly positive. So slightly positive from one molecule with the slightly negative from the other molecule, and the slightly negative from this with the positive this. So what do you call all of this together with their hydrogen bond connecting or attracting all these molecules together? This is water. Okay? So what's holding the water molecules to each other? Hydrogen bonds. The matter can be solid, can be liquid, can be gas. The solid have constant volume and shape. Okay? So you have this. The volume does not change. You can't do anything about it. And the shape does not change. The liquid, the volume does not change. I have a gallon of milk. If I put it in this container, it's a gallon of milk. If I put it in a cylindrical shape container, still a gallon of milk. Does it change? I put the gallon in another container. I put it in this container. It doesn't change, right? The shape does. The shape will take the shape of the container. Like if I put this gallon of milk in a cubical shape container, it will take the cubical shape. The milk will take the cubical shape. If I put it in a cylindrical shape, it will take the cylindrical shape. If I put it in a spherical shape, so the shape change and the volume does not change. Gas, both of them change. You can put a liter of a gas in this container, it will take the shape of the container, or this container, it will take the shape. And also the volume change, right? So you can put a gallon here, or a liter of oxygen, let's say, and you can compress it and make it half liter, but it's condensed, right? So both of them change in this case. The molecular weight of hydrogen is 1, oxygen is 16, H2 is 2, and hydrogen is 18. Now we're going to talk about the chemical reactions. The reactants are the materials that goes into the reaction. I have sodium here, I have chloride here. Those two are called the reactant. The product is what's coming out of the reaction, which is, in this case, what's the product of sodium and chloride, the two reactants? Table salt or sodium chloride. This is called the product. Metabolism are all the reactions that occur at one time. So if I'm looking at you and I'm monitoring your reactions, at this second, all reactions happening in your body at this point of time, this is called metabolism. Okay, energy is the power to do work. Work is a change of mass distance. Kinetic versus potential. This is versus chemical energy. Kinetic is energy of motion. Potential is the stored energy, and the chemical is stored in a chemical bond. The reactions can be catabolism or anabolism, decomposition versus synthesis. Okay, so if I get 1 plus this one, I put them together, or this and this. This is 1 and this is 1. I put them together to make 1. If this is anabolism or catabolism, if this is synthesis or decomposition, when you have 2 and put them together, you're synthesizing something. Okay, I have sodium, I have chloride. I put them together. I'm synthesizing sodium chloride. I have some hydrogen, have some oxygen. I put them together. I'm synthesizing, anabolizing. It's anabolic. So when you put A plus B, you give AB. This is synthesis. When I do the opposite, I give here sodium chloride together, separate it. This is called decomposition or catabolism. And catabolism basically means breaking down. Okay? So synthesis, which is anabolism, means building. Two small compounds, you put them and make one large. You know what's glycogen? What's glycogen?
Sugar.
Sugar. And it consists of what?
Glucose.
Glucose. A lot of units of glucose. So glucose plus glucose plus glucose plus glucose. This is glycogen. What do you call it when you put all these glucose units together and make one large glycogen? Anabolic or catabolic reaction? Anabolic. What if I get this glycogen and start to separate the molecules of glucose? What do you call this? Catabolic. Catabolic or decomposition. Okay? If you are going to break down something using water, you call it hydrolysis. Hydrolysis. Hydro means water. Lysis means breakdown. So it's breakdown by adding water. Are we following? Hydrolysis. Always try as we go. When you see a word, cut it into two or three pieces, and it will give you the meaning. Hydrolysis. Hydrolysis. Hydro means water. Lysis means breakdown. So what's hydrolysis? Breaking down using water. Okay? The opposite is dehydration synthesis. What's dehydration? D means? Yes. So you take water out. When you take water out, you synthesize. So this is called dehydration synthesis or condensation. Okay? Are we following? So hydrolysis versus dehydration synthesis, all right? Hydrolysis is you add water. Dehydration synthesis is when you lose water. And just to make it closer to your mind, let's do it this way. Can you hold this for a second? Okay, I'm holding one oxygen here. He's holding two hydrogen, okay? We wanted both of us to come together, react. You can't. You have to make me needing him in something, and he should need me in something, so we can react. How about this? You take the oxygen from me, you take the two hydrogens from him. What I'm missing now? I miss me only. What did I miss? And what did he miss? Now I need you to get the oxygen from me. And you need me to get the hydrogen from me, so we have to stay together. How about this? Look at this. We are together now, right? Break down. No, I can't. I need oxygen and have to stay with him. He needs hydrogen. Okay, here is your oxygen. Go away. Here is your hydrogen. Go away. Separate. So when you add water, you break down. When you take water out, you build. And this is what hydrolysis and dehydration is all about. Did you get this? Exchange, on the other hand, is when you have a compound and another compound, and you break it down and you change. So it's not like A, B, C, D, and then you put them together, A, B, C, D. No, A, B, C, D, and then you change. A, D, B, C, for example. This is called the exchange reaction. This is another type. Some reactions are reversible, means it goes both ways. So you can make it and break it, for example, and some others are irreversible. Once you do it, you cannot reverse it back to what it was. H is obviously one atom of hydrogen. O is one atom of oxygen. 2H, two atoms of hydrogen. Two atoms of oxygen is O2. H2 is a hydrogen molecule. O2 is oxygen molecule. H2O is water. So I want you just to know what each one of those means by itself, like HO, 2H2O, and H2O. What each one of those means. Now the enzyme. The enzyme is a catalyst, a helper that help to lower the activation energy for reaction. Which means like this. Just an example to make it clear what the enzyme is doing. Let's say you are driving your car, okay, and you got a flat tire for some reason, okay? You stopped, you get the spare tire, and you're trying to change it, you don't have tools, okay? So you start to use like a rock or something, and you get a piece of iron or something and try to work around. You can work for 5-6 hours just by using any tools, primitive tools that you have in your car, because you don't have enough tools, okay? And you will spend 5-6 hours time, and you will be, by the time you're done, you will be exhausted. You're spending a lot of energy, okay? This is one scenario. The other scenario is your car got a flat tire, and I come to you, do you need help? Yes. I need to change my tires. Okay, here is the hydraulic machine. Just do it like this. Put it. Okay? This will save you time and energy. This is the enzyme. Like if I give you a hydraulic machine to use it, it will take you 5 minutes to change the tire, right? This hydraulic machine that's saving you time and energy, this is the enzyme. So what's the enzyme? It's a catalyst that lower the activation energy. You need less energy to do the same job. Like when I give you the hydraulic machine, you do less effort in order to change the tires, okay? This is enzyme, lowering the activation energy for the reaction. Some reactions are called exergonic, which are the reactions that will end up producing energy. Okay? Each reaction usually use some energy and end up producing some energy. Depending on how much did you use and how much did you produce, I will call you exergonic versus endergonic. So if you use 5 units of energy and you end up producing 10, you're exergonic. If you use 10 and you end up producing 5, you're endergonic, okay? Or if you want to take it like a practical example, you are a worker, okay? And I give you $10 a day, okay? So you work for 5 days. How much did you cost me? $50. But you make a profit for me by taking the $50. You're making $100. Is that good? It's good. Did you make more than what you take? I spent $50, your salary, and you end up giving me $100. This is productive, right? So you produced more than what you used. So you as a worker, you're exergonic. I give you money, yes, but you give me more, okay? What if I give you $50 and you give me $50? That's nothing. That's equal. What if I give you $100 or $50 still and you produced 40? I will fire you, right? I will fire you. Why? Because you're endergonic. You're using more than what you're producing. Practically speaking, in the body, you need both of them. Some reactions, even though it costs you more than one they produce, but you have to have it. You have to use it. Something like building glycogen, for example. It does use some energy more than what it produces, but you have to store it anyway. So the body, practically speaking, in the body, you need both of them. But just understand what it's exergonic, which is ectothermic, versus endergonic, which is endothermic. If you spend or take energy more than what you produce, you're endergonic. If you take less and produce more, you're exergonic, productive. You give me more than what you cost me. Nutrients is the molecules that we get from food. Metabolites is the end product, or the broken down. Molecules can be organic and inorganic. And you need to remember this. When you call a compound or a molecule, when you call it organic or inorganic. You call it organic if it contains carbon and hydrogen. Okay? So is water organic or inorganic? But you have hydrogen. But no carbon. You have to have both of them. Actually, but this is not in physiology. Organic usually means actually carbon. Carbon. But if we're talking about the body, the actual body, our body, we're not talking about organic chemistry. We're talking about biochemistry. So inside your body, it's always carbon and hydrogen. You don't have carbon by itself. Okay? Carbohydrates, protein, lipids, and nucleic acid are the 4 known organic molecules in the body. So obviously, all of them contain carbon and hydrogen. And we will learn how to look at the formula, the simple way, and you can tell me if it is carbohydrate or fat or protein. There are some differences. What's in common? All of them are organic, meaning all of them contain and hydrogen. We're talking about biochemistry, okay? Don't worry now about organic chemistry. It's not carbon. Yeah, carbon in organic chemistry. I'm talking about biochemistry in your body. In your body. What's in common between those 4? All of them are organic and all of them contain carbon and hydrogen. How to know them from each other, we will cover that soon. When you talk about solution, this is when you mix 2 or more substances together until they become uniform mixture. Okay, so you get some salt, table salt, put it in the water and stir, keep on stirring until you don't see any salt. This is uniform mixture, right? If you just do that a little bit and you have some salt, it's not uniform, not yet. So solution is a uniform mixture of 2 or more substances. The medium, which is the water in this case, is called the solvent. The substance, which is the salt in this case, is called the solute. Remember this because we will build on it later on. What do you call the water? If you have salt dissolved in water, what do you call the water? Solvent. What do you call the salt? Solute. What do you call the water with salt dissolved? Solution. If the water can dissolve something, you call it soluble or water soluble. Is the salt water soluble? Yes. Sugar, is it water soluble? Oil? No, it's not water soluble. When you put water on something, how is it going to dissolve? The water will form a sphere. So what's practically speaking, if you look under the microscope and see what is the salted water, or when you dissolve salt on the water, you see molecules of sodium chloride surrounded by a sphere of water, and another molecule surrounded by a sphere of water. We don't see that because this is microscopic, but this is actually what's happening. The sphere, hydration sphere around each one of these ions. Something like this. Hydration sphere. Sodium chloride. Are you guys familiar with this? What's K? Potassium chloride, sodium chloride, calcium phosphate. Okay. Just be familiar with the names. So we talked about the organic compounds, which are the compounds that have both carbon and hydrogen, both of them together. Electrolytes are inorganic compounds, or inorganic ions, I'm sorry. Inorganic ions. What ions means? We just mentioned. When you lose or gain. When you lose or gain, I called you ion. Okay? So electrons are inorganic ions that conduct electricity. And the electrolytes in our body, it should be homogeneous way. So we have to have electrolytes that you have to have this amount of sodium, this amount of chloride, and so on. Otherwise, it will be called electrolyte imbalance. It's not balanced. Anything that dissolves in water, you call it hydrophilic. What's philic means? Love. Yeah, likes water. So like salt and sugar. Hydrophobic means, phobic means fears. So if it fears water, you call it hydrophobic. Like oil and fat, anything that's fats. So if is the fat polar or unpolar or non-polar? Non-polar, and that's why it does not dissolve in water. If it dissolves, it has to be polar. What do you mean polar? I mean unequal sharing. And that's why the water is coming together. How the sodium chloride dissolved with water? You have slightly positive and slightly negative that will react with the sodium chloride and surround it. This is what hydrophilic means. So for something to be hydrophilic, it has to be polar. Anything that's non-polar is hydrophobic. Are we following? It's so the fat is hydrophobic. Why? It does not react with water. Why? Because it's non-polar. It doesn't have this slight positive or negative like water. So it cannot react, cannot dissolve. Now pH. I mean the colloid. Colloid suspension and concentration. Colloid is a solution that have very large molecules, like blood plasma. If you get the what's the blood plasma means? This is the fluid part of the blood. So it's blood minus cells. Okay, fluid part. So if you get this and look under the microscope or magnifying lens or something, you will see large particles. I'm not talking about the cells. Okay, you remove the cells from the blood. The remaining part is called plasma. Okay, if you look at the plasma, you will see large molecules that are suspended and that are within the water. So this is called colloid. Suspension is when you have particles that settle down. It's not homogeneous. It's not equally distributed. This is like, did you ever use medication as a suspension, or you give it to the kids or something? Did you see it before?
Yeah.
Suspension, like antibiotic or something.
Yes.
What do you tell you?
Shake.
Shake it well, right? Before you use it. This is a suspension. So the suspension will have suspended elements, okay? Sedimentation. It's settle down. Just leave it for some time. It will settle down. The particles will go to the bottom and will settle down. And that's why they always tell you, if you're using a medication that's suspension, they always tell you shake well before using, right? We're all familiar with this. Why? Because it's suspension. If you leave it for some time, it will sediment, it will sit down at the bottom, and what you're actually giving the child is just this water part. You're not giving the active material, that sediment. So you have to shake it well to be equally distributed. Leave it for half hour, it will settle down again. This is suspension. Concentration is the amount of solute in the solvent. So if I ask you what's the concentration of salt, you tell me this is a liter of water and we have 5 grams. So the concentration is 5 grams per liter, right? If you put 10 grams, it's 10 grams per liter. So you have it's something compared to something, okay? And usually it's measured by mole per liter or milligram per milliliter, and this is the concentration. And for your information, when we go further, you will understand that it's all about concentration, not amount. Meaning, if I tell you that potassium level in the blood is 4, it does not mean the amount is 4. It means 4 milligram per milliliter. This is what it means. Okay? So we talk about concentration. If it's not about amount. Okay? We don't know the amount. That's too hard to describe it or to count it. So always talk about concentration. Okay? When I tell you 4, you have to 4 in what? 4 what in what? So it's all about concentration. If the concentration change, okay, Or let me say it this way. If I have 5 grams of salt in 1 liter, and I have 10 grams of salt in 2 liters, which one is more concentrated?
First one.
5 in 1 or 10 in 2? It's the same. It's the same concentration. 5 grams in 1 liter, 10 grams in 2 liters, 15 grams in 3 liters. Is it different? It's not different. It's the same concentration. It's 5 in 1 or 10 in 2. It's the same thing, right? So it's the same concentration. Is it the same amount? No, it's 5, 10, 15. This is not the issue. When you talk about the body, you're talking about concentration. It's all about ratio. 5 doesn't mean the amount is 5. It's a concentration. Okay? So any numbers that you will see from now on, it's all about concentration. Sodium, chloride. Anything is all about concentration. pH. pH, for some reason I always see it confusing when it comes to low pH versus high pH, which one is acidic, which one is alkaline. I always see confusion. Even 234 students still until almost to the end. Some students confused about which is which. The pH is not the H. The pH is not the hydrogen concentration. That's not true. Okay? Hydrogen, the amount of hydrogen in a solution produce acidity. Are you familiar with acidity and alkalinity? Hydrogen makes the solution acidic. Hydroxyl or bicarb will make the solution OH basic or alkaline. Yes. So the more hydrogen you have, the more acidic. The less hydrogen, the less acidic. Okay. pH is not the hydrogen concentration. The pH is a mathematical equation that means minus log hydrogen ion concentration, and I'm not worried about the calculations now. What I want you to know is the pH. They came with the way the reason why they did the pH. They tried to do the concentration of hydrogen, and they found it something like 10,1555. It's like a huge number. So they say, okay, let's do minus log the hydrogen ion concentration, and we get to an easy to remember number. So 7.4, which is our pH, is not hydrogen concentration. It's a mathematical equation. I'm not asking you to know the equation or how it goes. Just know that it's not the hydrogen concentration. It reflects somehow, but it's not the same. We're not talking about hydrogen concentration now. So the pH is reflecting the acidity versus alkalinity, and we start from 0, pH of 0, to the maximum of 14. What's exactly in the middle? 7, which is neutral. 7 is neutral. What's our body pH? Is that acidic or alkaline or neutral? Yes, because I always hear neutral, bodies have to be neutral. No, it doesn't have to be neutral. It is slightly alkaline. There is a difference between neutral and physiologic. Neutral only means 7, exactly in the middle. Between 0 and 14 is 7. This is neutral, and this is, by the way, it's only pure water. This is the only thing on earth that's actually 7. Pure water, 7. Okay? The only thing that we actually know is pure water. Is our blood pure water? Of course not. So it's not 7, because it goes like neutral body. No, it's physiologic. Physiologic can be anything. Can be acidic, can be alkaline, but practically speaking, it is slightly alkaline. It's not like 12 or 13. This is alkaline. 7.4 or 7.35, 7.45 is slightly alkaline. Okay, so this is normal pH, and I want you to remember the 7, which is the pure water, the 7.35 to 7.45, And this is the last thing that I'm going to talk about. And again, I don't know why it's confusing, but when you go under 7, is it acidic or alkaline? If you go above 7, so what's 8.4? Alkaline. 6.5? Acidic. Okay. So when you say acidic, means you're adding more hydrogen or less hydroxyl or OH, and the basic is the opposite, low hydrogen and high OH. And the way I think of it is, if I give you black and white paint, and I ask you to make it perfectly gray, 50-50, you put exactly the same, right? If you want to make it darker gray, you either add a little bit more black or less what? White. So you're playing with two components, not just one. So if you wanted to make it acidic, add hydrogen or subtract OH or both of them, right? And vice versa. And we will stop here.